Now we're not only going to solve partial differential equations, but we'll now solve partial differential equations with boundary conditions. So we're starting to solve boundary value problems, BVPs. And the first example will be this heated rod problem. Kind of help get some intuition into what the equations mean. So we have this rod of finite length. It goes from x equals 0 to x equals L, where x is distance along the length. We assume that this rod has the same area all the way along. It has the same density all the way along. We assume no heat escapes out the sides. It's insulated out the sides. So the only heat flow can be in the x direction. And take my word for it. By the way, I kind of derived this from the physics in my written up lecture. By the way, if you want that, email me. But the partial differential equation is written this way. We use a function of two variables, the distance along the rod and time, t, where k has to be greater than 0. We're going to add to that some boundary conditions. And in our first example, we'll say that the temperature, by the way, U stands for the temperature in the rod. We'll say the temperature at each end is held at a temperature of 0. Those are our boundary conditions. So there's the partial differential equation. These are the boundary conditions. The other condition is that it has a certain initial condition. So that the initial temperature, meaning at time t equals little t equals 0, it's some given function of distance along the rod, f of x, some f of x. So this whole problem is our boundary value problem. T has to be greater than 0, by the way. So we start the problem at time 0 and then see what happens as time goes on. That's the problem. So let's start using our product method, where we say U is a product of the two variables independently, function of each variable independently. Here I go through a more painful description of what it means. Let's see, what do we have? U sub xx, which is ultimately going to be x double prime t. We have a U sub t, which is ultimately going to mean x t prime. Here's what's going on. You shouldn't have to go through all this thinking each time you do it. You should be able to go from this to that without too much thinking. So that our equation now becomes this in the separated function. Then we do our algebra. I'll divide by k xt. Let's see, that'll get rid of the k's here and the t's here. On the right side, we'll get rid of the x's. At this point, we have separated the variables. We'll set them equal to the same separation constant. We have these two ordinary differential equations. We actually just solved these same equations in the previous recording, an example, what I call example 4. So we don't have to go through all that again. The t equation has this solution, and the x equation has different possible solutions depending on what lambda is. And now I do want to use the hyperbolic trig because our x has a finite extent. That's when we use the hyperbolic form of the equation, this equation, when lambda is negative. So now let's get to the boundary conditions, because we also have to separate variables for the boundary conditions. And let's see, we had a condition that where x equals 0, the temperature equals 0. Well, this u at x equals 0 means this. X times 0 times t for any time t must be equal to 0. And since it must hold for any time t, and it can't just be 0 for all time, because we have this initial condition, that requires that x at time, at argument 0 must be 0. Similarly, where x equals L, in separated functions, it means this. And again, for this to be 0 for all time t, x at argument L must be 0. The initial condition at time t equals 0, well, that must equal that initial condition. So we have to solve this guy, and we have to reject trivial solutions, or we have to reject just x equals 0 everywhere, assuming this initial condition is not just 0 everywhere. Which is going to lead us to the eigenvalue problem. We had the 3 solutions, depending on what lambda was. But now we've got boundary conditions. So let's take each solution and run it through our eigenvalue problem type logic. So here's the solution if lambda is negative. But we also had this initial condition, this boundary condition on x. When the argument was 0, we just got a, and that had to equal 0, which leaves us with b sinh alpha x. X equals L, that is b sinh alpha L. That has to be 0. Only way for this thing to be 0, sinh alpha L is never 0 for an alpha other than 0. B must be 0, which leads us to a trivial solution, and we reject it. By the way, we're going to see this exact problem. You know, this x differential equation with these boundary conditions. By the way, that's a Sturm-Liouville problem, but it's also going to be a familiar ordinary differential equation we're going to begin just doing automatically. We're not going to resolve it every single time we encounter it. In fact, we've already encountered it before, but we'll go through it again here. So for the negative lambdas, we reject the cases because they're all trivial cases or solutions of 0. When lambda at exactly equals 0, that means x function this a plus some bx. At the argument 0, that just says a, that must be 0. That only leaves us with the bx. And at the argument L, that means bl equals 0. L is not 0. So again, b must be 0 and a must be 0. Get a trivial solution, and we reject that as well. Finally, lambda greater than 0. That leads to this solution. At x equals 0, I get a. This sign of 0 is 0, so a equals 0. I'm left with b sine alpha x. Argument of L, that means b sine alpha L. That must be 0. Aha! Here, sine of alpha L equals 0 in a whole bunch of places, an infinite number of places. Every place the argument is an integer number of pi. Our alpha n's, there's going to be a bunch of alpha n's. N L, n pi. So our alpha n's are n pi over L. Our surviving function was sine of alpha x, so it's going to be sine of n pi x over L. Alpha was n pi over L. And I'm going to get this for all positive integer n's. So I have my eigenvalues, which are these alpha n squared, these n pi over L quantity squared. My eigenfunctions, which are these signs. We use the eigenvalue problem. How much farther we get? We're already kind of over 10 minutes. I'll continue with this problem in another recording.